Welcome to an explanation of the planimeter by Peter Lees and Kyle Gracer. A planimeter is a very simple device. The first part is the two arms shown here. There is an anchor point at one end, shown at the origin, a joint between the two arms, and a pointer currently shown at the corner of the rectangle. These components allow the planimeter a limited range of motion, a few positions of which are illustrated here. To help explain the planimeter mathematically, we will call the origin 0, 0, the joint AB, the pointer XY, which can be defined in terms of A and B, and the lengths of the arms as R. We will also assume that the angle between our arms is always the angle less than pi. This vector arrow, what I will call the wheel vector, indicates the direction that our wheel faces perpendicular to the second arm. This vector is x minus a, y minus b. We can now describe the field of wheel vectors in terms of x and y. We will call this field f of x and y, and it can be further broken down into its components p of x and y and q of x and y. Instrumental to understanding how a planimeter works is Green's theorem. Green's theorem is a lot like Stokes' theorem, which we learned about earlier, except it applies more specifically to two dimensions. So what it does in its general form is it equates the circulation around some closed shape, which is known as the line integral of a field projected onto the unit vectors of this line. So it basically is, in simple terms, how much of the field moves along the path. It equates that, the circulation, to the curl of that vector field that this shape is in, times the area of the shape. This is very useful to anyone trying to find the area of any two-dimensional shape, as we are doing.
So let's look at the curl of this vector field. The curl is just the cross product of the gradient times the equation for the vector field. And there's no r term here, so we're just looking at p and q, and we'll find the curl is equal to the partial of q in terms of x minus the partial of p in terms of y. And if we use the second equation from above, we can find that curl to be equal 2 over r plus negative a partial x minus b partial y over r. And so if we look at our planimeter and change the sign of this equation, we can find that we're just looking for a partial x plus b partial y, because that is the arbitrary term point that we picked between x, y, and 0, 0, r away from both. And so to do that, a couple important things. We can use the Pythagorean theorem to note that x minus a squared plus y minus b squared is equal to r squared, and a squared plus b squared is equal to r squared. And so we can refactor that and get that x squared minus 2ax plus y squared minus 2yb equals r squared. And remembering that a is equal to plus or minus the square root of r squared minus b squared, and the opposite for b, we can plug in either a or b as these square roots to change the equations around and either get rid of a or get rid of b. And then doing that, we can find the partial in terms of x for the one with only a's, and the partial in terms of y for only b's. And we're going to look at the one with a's here. So when we partial it, we get this equation. And with a little refactoring, taking out the partial of partial of a in terms of x, we find that a partial x is equal to 2a minus 2x times 2 root r squared minus a squared over negative 4x root r squared minus a squared minus 4ay. And then we can do a similar thing for b and partial y and get a partial x plus b partial y equals this. And then remembering again what a and b equal, the square roots of r squared minus b squared, or vice versa, then we can put that back in, put b's and a's back in the equation, and refactor it a little bit, and eventually come down to one fraction, because they're both over 4ay minus 4bx. Combine the two, and after a little bit more factoring, we get that a partial x plus b partial y is equal to 1. And using that, we can find that the curl which is equal to 2 over r minus a partial x plus b partial y over r is actually equal to 2 over r minus 1 over r, which is equal to 1 over r.
We've just proven that the circulation, this term of our Green's theorem, is equal to the wheel rotation. We know that this is equal to the curl times area, and Kyle just proved that curl is always 1 over r. This is extremely useful to us as we get that scale factor times wheel rotation is equal to area. This can be determined experimentally, and there you have it.